Every year, the global glass mirror market generates approximately $4 billion. To support an industry of this size, enormous quantities of glass and silver must be processed. But how are mirrors actually manufactured inside factories? To find out, we are traveling to China, the world's largest producer of mirrors, to visit one of its factories. The history of mirror making stretches back thousands of years. The earliest mirrors used by humans were simply the surfaces of calm water or polished pieces of obsidian, a dark volcanic rock capable of reflecting light. Over time, ancient civilizations such as the Egyptians and Romans began producing more sophisticated mirrors. They used discs made from bronze, copper, or silver, polishing the metal repeatedly until it developed a reflective shine. During the Middle Ages, mirror making advanced with the introduction of glass covered by a thin layer of metal. However, it was during the Renaissance in Venice that the technique was perfected. Venetian craftsmen applied mercury to the back of glass, creating mirrors that offered clearer and more accurate reflections. The process was considered so valuable that Venetian manufacturers kept it a closely guarded secret for centuries. In the 19th century, the chemical silvering technique developed by Justus von Liebig revolutionized mirror production. Instead of using mercury, manufacturers chemically deposited a thin layer of silver onto the glass. This safer and more efficient method marked the beginning of the modern mirror as we know it today. So how does a solid metal eventually become part of a mirror? Before the reflective coating can be added, manufacturers must first produce the foundation of every mirror, the glass. Glass production is a process that combines science, heat, and extreme precision. It begins with the careful selection and mixing of several raw materials. The main ingredient is silica sand, a fine and slightly shiny material that forms the essential structure of glass. However, silica sand on its own requires extremely high temperatures to melt. To make the process easier, sodium carbonate, also known as soda ash, is added to the mixture. It acts as a softening agent by lowering the melting point of the silica. Limestone is also added. It gives the finished glass additional strength and durability, making it less likely to break, deteriorate, or wear down over time. Once the exact proportions of these materials have been measured, they are mixed thoroughly and poured into an industrial furnace capable of reaching temperatures above 3090 degrees Fahrenheit. Under this extreme heat, the solid ingredients melt together and transform into a glowing, viscous liquid that resembles molten lava. This liquid will eventually become the glass used to produce the mirror. The melting process must be controlled very carefully. Even a small variation in temperature or composition can create bubbles, distortions, or other imperfections inside the glass. While the material is still molten, it is spread into uniform sheets using large industrial rollers. This stage is critical because it determines the thickness, consistency, and surface texture of the glass. Once shaped, the glass must begin cooling. However, it cannot be cooled suddenly. If hot glass cools too quickly, internal stress can develop inside the material. These hidden stresses may cause it to crack, break easily, or develop defects later in the manufacturing process. To prevent this, the glass moves gradually through a controlled cooling system. Special rollers and cooling equipment slowly reduce its temperature, allowing the material to stabilize evenly. At the end of this process, the result is a strong, perfectly smooth sheet of glass, ready for the next stages of mirror production. The next stage on the production line is cutting. This is a meticulous process that transforms the large, cooled sheets of glass into pieces with specific dimensions. The required measurements depend on the final type and purpose of the mirror. The process is highly automated. Precision cutters, blades, and rollers move across the glass, producing clean edges and accurate cuts. Every movement is carefully calculated to minimize wasted material and prevent cracks or fractures. After cutting, the glass moves into the polishing stage. Here, machines remove any small imperfections, uneven areas, or irregularities from its surface. This step is extremely important. The metal coating that will later create the reflection can only be applied properly if the glass is completely smooth. An uneven surface could prevent the coating from adhering uniformly, resulting in a distorted, cloudy, or unclear reflection. Once polished, the glass undergoes a deep cleaning process. Special chemical solutions remove every trace of dust, grease, oil, and microscopic residue left behind during the previous stages. This intense level of cleaning ensures that no particles interfere with the coating process. At this point, the glass is completely smooth, clean, and ready to receive its reflective layer. The application of that reflective layer begins with one essential material: metallic silver. Silver is known for its exceptional ability to reflect light, but before it reaches the glass factory, it must first be extracted and refined. Silver is rarely found in a completely pure form in nature. Instead, it is usually extracted from ores containing silver compounds. One example is galena, a lead-based mineral that often contains traces of silver. Another is argentite, an ore rich in silver sulfide. Interestingly, much of the silver used around the world does not come from mines dedicated exclusively to silver production. Instead, silver is frequently recovered as a byproduct of mining other important metals, including gold, lead, and copper. This allows mining companies to make better use of the available resources and make silver production more economically efficient. Once silver-bearing ore has been removed from the ground, it must go through a complex refining process. The goal is to separate the silver from unwanted minerals and impurities while achieving a very high level of purity. Several methods can be used, but two of the most common are cyanide leaching and electrolysis. The first method, cyanide leaching, is a chemical process widely used to extract silver and gold from ores containing relatively low concentrations of precious metals. The ore is first crushed into a very fine material. Breaking it into smaller particles increases the surface area and allows the silver to come into greater contact with the chemical solution. The crushed ore is then mixed with a diluted solution of sodium cyanide or potassium cyanide. This solution dissolves the silver and creates a soluble compound known as silver cyanide. Oxygen is introduced to accelerate the chemical reaction and improve the efficiency of the extraction process. However, cyanide is extremely toxic. For that reason, facilities using this method require strict safety procedures. Despite these limitations, cyanide leaching remains valuable because it can recover precious metals efficiently, even from low-grade ores containing only small amounts of silver. The second major refining method is electrolysis, a process that uses electricity to purify silver that has already been extracted from the ore. First, the process material is placed in an electrolytic solution, usually containing silver nitrate and water. Two electrodes are submerged inside this controlled system. The anode is made from impure silver, while the cathode is a metal plate or bar onto which the pure silver will be deposited. When an electric current passes through the system, silver ions separate from the impure anode and travel through the solution toward the cathode. There, the ions accumulate and form a new layer of extremely pure silver. At the same time, many of the impurities from the anode fall to the bottom of the container. This residue is known as anode sludge. Although it may sound like waste, anode sludge can contain other valuable metals, including gold and platinum, which can later be recovered through additional processing. Electrolysis produces silver with an exceptionally high level of purity. It is also a controlled and efficient process, making it an important technique in modern metal refining operations. Once refining is complete, the silver is ready for industrial use. It is often formed into ingots, which are compact blocks that can be transported and stored easily. It may also be produced as small grains or pellets that factories can melt or dissolve, depending on their manufacturing requirements. One of the most common applications for refined silver is mirror production. Because silver can reflect nearly all visible light that reaches it, it is an ideal material for manufacturing high-quality mirrors with bright, sharp, and accurate reflections. Back on the mirror production line, the pure silver is transformed into a specially prepared chemical solution that can be deposited onto the surface of the glass. This stage is known as chemical deposition or chemical silvering. During the process, silver compounds react with other chemicals, including ammonia and glucose. The controlled reaction causes an extremely thin layer of metallic silver to form directly on the previously polished and cleaned glass. The transformation almost appears magical. A transparent sheet of ordinary glass gradually becomes a reflective surface capable of reproducing images with remarkable accuracy and clarity. However, silver by itself is sensitive to external conditions. Exposure to oxygen, moisture, and certain chemicals can cause it to tarnish or deteriorate, reducing its ability to reflect light. To prevent this, additional protective layers must be applied over the silver. First, the factory adds a layer of copper. This copper coating acts as an extra shield, helping protect the silver from moisture, oxidation, and corrosion. Specially formulated paints or protective varnishes are then applied over the metal layers. These coatings strengthen the back of the mirror and provide greater durability. The final result is a carefully constructed reflective surface in which pure silver, sealed beneath multiple protective layers, transforms ordinary glass into a durable mirror that combines function, appearance, and manufacturing technology. Once the layers of silver, copper, and protective coating have been applied, they must be dried and hardened completely. The glass sheets travel through a special industrial oven, where controlled heat helps the coatings bond securely to the surface. This step is essential. The heat not only dries the silver, copper, and protective paint, but also makes the layers stronger and more resistant. Proper curing ensures that the mirror can withstand years of use and exposure to changing environmental conditions. Without this hardening process, the coatings could wear away, separate, or deteriorate much more quickly, significantly reducing the mirror's useful life. Once the layers have hardened, the mirror moves to quality inspection. Every sheet is examined carefully to ensure it meets the factory's standards. Inspectors and automated systems search for defects such as air bubbles trapped between layers, stains on the surface, scratches, distorted areas, or sections that were not coated correctly. These imperfections could affect both the appearance and functionality of the mirror. Products that fail to meet the required standards are rejected and sent for repair or recycling. This ensures that only mirrors of acceptable quality continue toward the final stages of production. The next stage is final cutting and optional framing. The mirrors are cut into exact sizes according to customer requirements or industry standards. These dimensions depend on the product's intended application. A mirror may be produced for a bathroom, bedroom, automobile, commercial building, medical facility, or industrial environment. If required by the design, decorative edges or frames can also be added. Frames do more than improve the mirror's appearance. They can reinforce and protect the edges of the glass while giving the finished product a more elegant and complete appearance. The framing material may be wood, metal, plastic, or another manufactured material. The final choice depends on the mirror's style, price, intended use, and the customer's preferences. Finally, the completed mirrors are packaged with great care. Packaging is essential because mirrors are fragile and can crack or shatter if they are dropped, struck, or handled incorrectly during transportation. Protective materials such as foam, cardboard, plastic wrapping, and reinforced corner guards are used to keep the mirrors secure. For larger mirrors, factories may use wooden supports, crates, or custom packaging designed to prevent the glass from shifting while it is being transported. Once packaged, the mirrors are shipped to distributors, retailers, construction companies, vehicle manufacturers, or final customers. They are now ready to be installed and used in an enormous variety of applications. And that is how millions of mirrors are produced around the world. What did you think of the process? Let me know in the comments. If you enjoyed the video, click the like button and remember to subscribe to the channel. You can also find more videos that may interest you on the screen right now. Choose one and continue exploring how everyday products are manufactured. Until next time.